Imagine two AI models tackling the same challenging problem. Qwen meticulously verifies each step, backtracks when necessary, and sets subgoals. Llama, on the other hand, charges ahead without these thoughtful strategies. The result? Qwen keeps improving, while Llama struggles to get better. So what's going on here? A recent study from Stanford breaks it down. Turns out reasoning habits, things like verification, backtracking, and working backward, are critical for self-improvement. Without them, a model just spins its wheels. And the cool part? We can actually teach models these habits through pre-training. That means AI that doesn't just memorize answers, but actively gets better at thinking. So, how do we make this happen? Let's dive in.
Imagine you're trying to solve a tough puzzle. You don't just guess once, you think harder, refine your approach, and keep iterating. Some language models do the same. Given more time to reason, they get better at solving tasks. But not all of them improve equally. Take this example. Two models, Qwen and Llama, were both trained with reinforcement learning on the same game. Over time, Qwen soared in performance, but Llama barely got better. Why? According to this paper, it's because Qwen uses certain cognitive behaviors, like checking answers, backtracking, setting subgoals, and even working backward, while Llama doesn't, at least not on its own. What's especially fascinating is that when Llama is trained using examples that show these reasoning strategies, it suddenly performs just as well as Qwen. Even if those examples contain incorrect answers, as long as they include the right reasoning process, Llama still improves. It's a huge hint that learning how to think can matter more than just memorizing correct answers. The researchers then tweak Llama's pre-training data to include more structured examples of reasoning. With this change, Llama rises to match Qwen's learning curve. The main idea is that a model's way of thinking from the get-go seems to decide whether it can benefit from extra training or reinforcement learning, or whether it'll just stall out. So why do some models, like Qwen, get better with training while others, like Llama, barely improve? The authors dig into that question by focusing on a math-based game called Countdown. Both Qwen and Llama are trained with reinforcement learning. Qwen naturally starts using verification, backtracking, and other strategies. Llama, on the other hand, doesn't do much of that on its own. But here's the twist. When Llama is trained on examples that demonstrate these reasoning behaviors, even if the final answers are wrong, it still ends up matching Qwen's improvement. Check out the figure here to see how performance scores change once models are exposed to structured reasoning. You'll notice that as soon as Llama sees these examples, its scores climb to Qwen's level. It's not the final correctness that drives learning, it's the process. This suggests that teaching a model how to think can be more effective than simply giving it correct solutions. And once Llama's dataset is specifically filtered to highlight these behaviors, it mirrors Qwen's improvement pattern. That's a big deal, because it means the key to boosting performance might lie in how we structure the model's reasoning. Humans don't solve problems in a single straight shot. We check our work, rethink our steps, break big goals into smaller ones, and sometimes work backward from the answer to see how it fits. The researchers call these four crucial behaviors verification, backtracking, subgoal setting, and backward chaining. They notice that Qwen already displays two of these, verification and backtracking, while Llama doesn't. So maybe it's not just about right answers. Maybe it's about the model's habits. To test this, they try 3 interventions. First, they give Llama synthetic examples that show these habits, and Llama suddenly performs like Qwen. Second, even feeding Llama incorrect solutions still helps, as long as the reasoning process is intact. Finally, they filter the dataset to emphasize structured reasoning, and, again, Llama's performance shoots up. In the latter part of this section, they compare different methods to improve a model's reasoning: external search, in-context search, and reinforcement learning. External search might let a model test multiple solutions, but it won't necessarily learn from past failures. In-context search refines a model's outputs, but needs carefully constructed prompts. Meanwhile, RL can help models develop their own strategies over time. The trick is balancing these approaches so the model can get the most out of each. Reinforcement learning, RL, should, in theory, help models learn how to think. But why do some models fail to improve at all? The authors argue that priming models with good reasoning behaviors makes a huge difference. Look at figure 2 here. The first 2 graphs show performance scores for Qwen, Llama, and primed versions of Llama. Normally, Qwen races ahead while Llama stalls. But when Llama is taught strategies like backtracking and verification, it quickly catches up. The last two graphs show how the primed models use longer responses, which indicates they're actually changing the way they think, rather than just spitting out quick guesses. They then zoom in on different RL methods, referencing early breakthroughs like DeepSeek R1, which demonstrated that even simpler RL approaches can dramatically improve structured reasoning. The core question remains, why do some models adapt so well through RL while others plateau? Finally, they describe the countdown game. It's a math puzzle, where you use basic arithmetic to reach a target. It's great for testing how well a model can break down problems, try multiple paths, and keep track of what works or doesn't. This sets the stage for the next batch of experiments. Now, not all AI models learn the same way. Some figure things out fast, while others never quite take off. The authors chose the countdown game because it demands real, step-by-step reasoning without the confusion of a massive search space. This makes it easier to see if a model is learning strategies or just memorizing patterns. They train both Qwen and Llama with RL using proximal policy optimization. Everything. At first, they're on the same level. Then, around step 30, Qwen starts doing way better, longer answers, more accurate calculations, until it hits 60% accuracy. Meanwhile, Llama hovers around 30%. Something about Qwen's approach changes. Early on, it explains each reasoning step. Later, it does silent checks, testing strategies internally without spelling them out. So what's the secret sauce? Why does Qwen figure out how to improve while Llama just limps along? The authors propose that Qwen starts with good reasoning habits. RL amplifies those habits, and Qwen takes off. The next part of the paper introduces a formal framework to analyze these habits, focusing on verification, backtracking, subgoal setting, and backward chaining. Models don't just learn facts, they develop habits of mind. This paper spotlights 4 that really matter: backtracking, verification, subgoal setting, and backward chaining. They give a model the flexibility to explore different strategies instead of marching straight to an answer. Because these behaviors can be tough to identify in raw text, the researchers train a classifier pipeline using GPT-4o Mini, which balances cost and performance. They run model outputs through this classifier to see how often each behavior shows up, and the data is clear. Qwen shows a lot more structured reasoning than Llama. Even a bigger Llama, with 70B parameters, doesn't reliably backtrack. It's a clue that if a model doesn't start with strong reasoning behaviors, then no amount of RL can magically create them. RL will only amplify patterns the model already has. If those patterns are weak or absent, the model won't improve much, no matter how hard you train it. Naturally, that leads to the question, can we inject these reasoning patterns into a weaker model? The next section explores how to do just that. So is it enough to just let a model think longer? Apparently not. It's about how the model thinks. The researchers test this by priming models with specific reasoning strategies. They create 7 datasets, each focusing on a different cognitive behavior, such as backtracking or verification, and some that combine multiple behaviors. They also create control sets where the model sees empty or meaningless thinking tokens, just to check if it's about length of reasoning versus actual structure. Training a model on empty reasoning tokens barely improves results. Qwen even does worse when it's forced to produce empty chain-of-thought text, but training a model with genuine examples of backtracking and verification leads to a major boost. That's because RL zeroes in on useful behaviors, like double-checking an answer, and strengthens them while ignoring random filler. The lesson here is that just asking a model to generate longer explanations doesn't make it smarter. It has to learn the right reasoning habits. Without that, more text is just more noise. One of the most surprising findings is that models don't even need correct answers to improve. They just need the correct way of thinking. Look at figure 6 here. Llama models primed with structured reasoning behaviors, but wrong final answers, still manage to catch up in performance. This means the process can outweigh simple correctness. What if we could bake these reasoning behaviors right into a model's pre-training, before RL ever comes into play? That's the next idea. The researchers look at big math data sets, Open Web Math and Fine Math, scanning thousands of documents for traces of verification, backtracking, subgoal setting, and backward chaining. Figure 7 shows how these behaviors are actually not that common in the data. So even when a model is trained on math-heavy text, it may not see enough examples of structured thinking. If it never sees verification or backtracking in its pre-training, it's unlikely to pick them up later just by chance. So the authors propose a shift. Instead of just adding more math data, why not inject more examples of systematic reasoning? If we want models to think better right away, The pre-training data has to emphasize reasoning behaviors. The authors do this by taking a carefully selected subset of open web math. They use Qwen -2.5 to 32b to classify how much structured thinking appears in each document. Then they rewrite each document in a question thought answer format if it contains enough signs of verification, backtracking, and the other key habits. A control version keeps minimal reasoning patterns. They pre-train LLAMA 3.2 to 3b on these two datasets. The result is dramatic. Look at figure 8 here. Models trained on behavior-enriched data match Qwen's performance, while the control model can't catch up. Even better, these newly trained models keep using structured reasoning during RL, instead of slipping back into guessy shortcuts. The authors wrap up with a big takeaway. Good reasoning behaviors are crucial for self-improvement. Just throwing more data or more training steps at a model isn't enough. You have to make sure it has the right thought processes, even if that means training it on examples with incorrect solutions. As long as the reasoning steps are clear, the model can learn from them. That's how you engineer self-improvement from the ground up. In conclusion, cognitive behaviors play a fundamental role in problem-solving and learning, both in humans and in AI. While this study focuses on structured tasks like countdown, the findings suggest that similar principles could apply to broader domains like coding, gameplay, or creative writing. Future research may explore how task-specific constraints influence reasoning behaviors, and whether AI models can develop entirely new cognitive strategies beyond what humans have designed. By guiding AI with structured reasoning, we may be setting the stage for the emergence of fundamentally new ways of thinking and problem-solving. Thanks for joining us today. Happy learning and stretching together.